We're now going to begin our third section of the lecture, picking up from where we ended up in section 2 on climate change and energy policy, and now begin to move into more health effects. As we can see here in this slide, this is a depiction of major environmental health events. This was compiled by the Harvard School of Public Health. And as you'll see on the background of this slide, you'll see the North Atlantic Oscillation and climate change events regressed against some of these major health effects. The blue graph that you see at the very back, those are harmful algal blooms, which have increased dramatically, as you can see, in the last 15 to 20 years. You'll also see that coral bleaching events, fish kills, shellfish harvest issues all have increased with dramatic increase in the last 15 to 20 years. So how are our coastal ecosystems doing? Since we said that in the last section how climate change effects are going to be most manifest in coastal areas because of the increase in urbanization. If we take a look at the Coastal Condition Report, which is our report card for how coastal ecosystems are doing, over 44% of all of our coastal areas are impaired by non-point source pollution. This is related to the change in hydrology we talked about earlier when we talked about urban areas. If we take a look at Suzanne Bricker's report, she reports that 2/3 of our estuaries and bays are moderately to severely impacted by eutrophication. And eutrophication is basically a factor in the environment where we have increased levels of nitrogen and phosphorus, which cause the harmful algal blooms we just talked about. We also see more than 13,000 beach advisories in 2001, and that number has increased to more than 35,000 in more recent times. And then finally, 40% of our shellfish harvest areas are impaired in some way due to increased runoff. So one of the things we can really say when we talked about paving paradise and putting up a parking lot is how this increased runoff manifests itself in major changes in landscape ecology which affect health. Nowhere are these health effects more manifest from urbanization and in the southeast U.S. The southeast U.S. is the fastest growing coastal region of the U.S., followed by the Pacific and Gulf of Mexico regions. The southeast U.S. includes the area from Cape Hatteras, North Carolina, to Cape Kennedy, Florida. The University of South Carolina has been involved in 3 major studies looking at the effects of urbanization in the southeast U.S. We have published 2 textbooks on this topic, Sustainable Development in the Southeast U.S., and then that was published in '96, and then our green book, Managing Rapidly Developed Coastal Areas, which was published in 2007, and then finally our Tidal Creek Project, which was published in about 2008. One of the things we found as we studied urbanization in coastal areas, the impacts are greatest not in the large major rivers or streams, but it's really in the little tiny tidal creeks, the headwater creeks, which are basically the nursery grounds for 86% of the finfish that we like to eat and the majority of the shellfish that we like to consume. So really, if you think about it in terms of your circulatory system, the health effects don't occur in your arteries or veins. They occur in these small capillaries, which really get clogged by pollution running off from land. This next slide just gives you a graphic representation of how rapidly these coastal areas are changing. The red slide that you see is the population growth in Horry County, which is where the Myrtle Beach Grand Strand area is. And you'll notice that beginning in the 1970s, we have population doubling times of around 25 years, going from around 100 to over 200,000 people in just a short period of time. The only other places in the world that have this rate of population growth are sub-Saharan Africa. And there we are not trying to maintain the quality of life or the standard of living like we are here in the U.S. So this poses tremendous burdens in terms of infrastructure development. If you think about it, your population doubling every 25 years. That means every 25 years you have to have double the numbers of doctors, nurses, lawyers, police, fire, sewer, schools. All of those have to double every 25 years, which puts a tremendous economic burden on these areas. And it also puts significant ecological pressures on these coastal ecosystems. This is a map of Charleston showing the change in urban footprint. Now, one of the things we have found, for every 1% increase in population growth, there is a 5% increase in urban land area. That's because rather than building up, we build out. It's what we call urban sprawl. So if you have a 20 to 25 year, let's just say a 20-year doubling time, like we see in Horry County, for population growth, your doubling time for changing the landscape ecology, that is paving paradise and putting up a parking lot, the amount of asphalt doubles every 5 years. So that has a tremendous impact in the amount of pollution and runoff that comes out of these coastal areas. So you can see in the Charleston area how we go from 70 square miles to 250 square miles in just a very short period of time from 1970 to 94. And you can see to 2015, it's over 600 square miles. So as you see, these numbers dramatically change. Now, one of the problems that we have with urbanization is that it's the way we build urban developments. What this slide depicts, on the bottom you have different size residential lots, and then you have it superimposed in these graphs the percent imperviousness on each bar. So you'll notice that any size lot less than 1 acre produces about 20% imperviousness. Now we know when imperviousness increases above 30%, we begin to stress ecosystems, and above that we begin to see loss of ecosystem services. So you'll notice that, like with an 1/8 acre lot or smaller, we see dramatic changes in the percent imperviousness up to 40-50%. So if we take a look at a typical forested area, when it normally rains, 10% of the rainfall falls off the land as runoff. You can see that as we increase the amount of imperviousness to 10 to 20% imperviousness, you'll see that the amount of runoff doubles from 10% to 20%. You'll then notice if we get into highly urbanized conditions, we can increase that amount of runoff all the way up to 500%. 50% of the rain runs off as runoff. Now, what makes this dramatic is that if we take a look at drought as a major effect of climate change, we are no longer storing water in groundwater where it's preserved to be used during drought, but rather we're putting it into surface ponds where it evaporates. So we lose this water at the very time we need to conserve it. This slide depicts what happens when you increase imperviousness. Anything above 20% imperviousness, we begin to see impacts on water quality and environmental condition. Anything above 30%, we then begin to see degradation of ecosystem services. Just to make a point here, and you don't need to worry about these numbers, these are the different concentrations of different pollutants that we see in urban runoff, all of which run into these receiving waters where they may impact the ecosystem services in these areas, including contaminating seafood and rendering waters unfit for recreational activity. Notice the very high levels of fecal coliform bacteria, over 10,000 bacteria per liter. Earlier I showed you the slide of the Urbanization in Southeast Estuary study, the Land Use Coastal Ecosystem study, and the Tidal Creek study, and the books we produced from those reports. Summarizing all that information into 4 slides is what I've done on this one 4-panel slide. So if we start at the left on the top, as you increase imperviousness, it is highly correlated with increase in population. If we move to the right at the top, as we increase imperviousness and move from a forested area to a suburban area to an urban area, we increase the amount of runoff off those systems. And if you think about runoff as like a garden hose, if you turn the garden hose on slowly and allow it to infiltrate into the soils, you do not wash much of the soil away and the water is contained. But if you think about putting a nozzle on that hose and spraying it wide open, the wider open the flow is coming out of the hose, the more soil you erode. Now, and that's what happens with urban runoff. As we erode more soils, attached to those soils will be chemical contaminants, microbes, and nutrients. So if we move to the bottom two panels, on the left, we see very high correlations between fecal coliform bacteria and imperviousness. And then on the bottom right, the same correlation for chemical contaminants with impervious cover. So impervious cover is what really drives urbanization effects and can cause loss of ecosystem services, such as fishability and swimmability. The very amenities that draw people to the coast are the first two things that are lost. And of course, these have very significant public health consequences. So this is a little conceptual model that sort of shows, as we look at the percent impervious cover in blue at the bottom, as we go from above 10 to 20% impervious cover, you'll see that we increase the exposure of the environment and humans to increased levels of nutrients, microbes, and chemical pollution. And by the time we get to 30 to 40% impervious cover, we get to the human responses, which are closed shellfish harvest areas and beaches which are no longer safe to swim. Now, if not, based on this, you can clearly see that urbanization, that is putting 5 times more people per land area and 5 times more industrial and commercial activity in the coastal zone, has dramatic consequences. But now we add climate change as another variable to consider that intersects with urbanization. So what I want to do is talk a little bit about that intersection, because where we're going to see climate change effects the greatest will be in these coastal areas. Many of you may have seen this slide, the red being the increased atmospheric concentration of CO2, the dark blue being the increasing CO2 content of seawater. And as we absorb CO2, it forms carbonic acid, which then lowers the pH, causing ocean acidification that we see in the light blue. This is the whole aspect of climate change that we have to consider. Now, as I talk about climate change, one of my co-authors on this talk is Dr. Tom Peterson. Dr. Peterson is a member of the Intergovernmental Panel on Climate Change. He's one of the representatives for the U.S. His office is located in Asheville, North Carolina. And so the data that I'm going to be presenting to you today are slides from Dr. Peterson on this topic. So they're authoritative and the best state of knowledge that we have on this topic. Now, this is a slide of CO2 emissions projected now and into the future with what they call the low and high CO2 emission scenarios. And these different CO2 emission scenarios assume certain reductions in the current CO2 discharge that we see due to climate strategies being implemented. One of the criticisms that people make of these different climate models is how reliable are they, and are they liberal or are they conservative? Dr. Peterson always likes to point out these models are extremely conservative. For example, you'll notice the top left panel, there's a little yellow box, and if we blow that box up, what it shows is that the current models, all 3 low and high and moderate emission scenarios, our current level of CO2 production is actually higher than any of the model predictions, which means these models are highly conservative. They are not overestimating the effect. They're highly conservative. The other thing about this slide Dr. Peterson would want me to remind you of is that roughly 1/3 of the CO2 burned from fossil fuels today will still be here 100 years from now. And 1,000 years from now, 20% of it will still be here in the atmosphere. So CO2 does not go away anytime soon if we are emitting it today. That's why action now is required in order for us to take steps to preserve the environment. Now, how may climate change affect health? Climate change may directly affect the growth, the survival, the persistence, distribution, transmission, and virulence of disease-causing organisms, primarily microbes, as well as organisms that cause harmful algal blooms and produce biotoxins that are some of the most toxic chemicals known to man. Climate may also affect disease vectors, such as mosquitoes and other insect vectors. And it may also have direct effects in terms of temperature, precipitation, that is drought or flooding, and sea level rise in extreme events. So I would like to start by talking about the threat from increased temperature. And one of the things we know is that this increased temperature will cause melting of polar ice. Now, a lot of us don't consider the fact that for the last 200, 300 years, since the Industrial Revolution, a lot of the air pollution that's been transferred into the atmosphere and basically transferred across the planet into those Arctic systems has been captured and sequestered in the ice in the Arctic. As we melt this polar ice, we're essentially going to concentrate 300 years of air pollution and basically melt a lot of it with the projected forecast of melting of a lot of the global polar ice, which means we're going to be releasing chemicals like mercury, lead, DDT, and other air pollutants into these northern boreal ecosystems around our poles. Now, one of the things that we know is that we have a tendency for some of the warming to occur disproportionately. It's not all at the equator, but rather it's more distributed poleward. And this slide sort of illustrates this. If you take a look at the two panels on the left-hand side at the bottom, they're the current rate of temperature change, which shows a couple of degrees Fahrenheit increase. But you'll notice as we look up at Alaska, you'll notice that the temperature changes are most dramatic and most significant increase in those polar regions. And then if we move out to later in the century, again, you'll notice those most dramatic changes are in those polar areas around Alaska, where we're going to melt ice. Now, when we begin to look at temperature effects, the number of days of temperatures above 100 degrees will dramatically increase. For example, Washington, D.C. on average has 1 day per year where it's above 100 degrees. We expect by the end of the century those numbers of days to be over 14 days per year. And that's not when Congress is in session. So if we add the days Congress is in session with that additional hot air, we may see even more. That was a joke. Now, if we take a look at Dallas, Texas, we'll see that the numbers go from 19 days per year to 78 days per year. You may remember last summer we had 42 straight days in Dallas of temperatures above 100 degrees, and we actually got close to 70 days above 100 degrees in Dallas. Now, what's significant about 78 days? That literally means all 3 months of the summer, the temperature is going to be 100 degrees almost every day during the summer. Not just some of the summer like it is now, but almost the entire summer. The other thing we know that these increased temperatures will have a dramatic effect on what we call the breadbasket of the U.S., where we grow most of our corn and wheat and other grains. That breadbasket will shift north into Minnesota and southern Canada, away from Nebraska and some of the lower states where we currently have a lot of Kansas, Oklahoma, those states. The other thing, and that's because the precipitation patterns are going to change as well as the temperature. The other thing that happens with a CO2 enriched environment, you decrease the protein content of your plants because they don't produce as much protein. The other thing we know is that weeds, your P4 plants, your P3 plants are your grains, your P4 plants are your weeds. They actually thrive in CO2 enriched environments. So what that means is your weeds will outcompete your beneficial crops, which means we'll have to use more herbicides. Similarly, because the crops produce less protein, in order for the insects to meet their protein needs, they'll have to consume more of the crop, which means we'll have to use more insecticides. So we don't think about these indirect effects of climate change as well. This slide sort of captures the whole essence of how temperature change associated with climate change and some of these other factors we've been talking about really takes a toll on the environment. This is a concept of what we call moving states. And so you can see on the left side of the slide, the climate of New England will become like that of Raleigh, North Carolina by the end of the century. Similarly, on the right side, we see the climate of Chicago, Illinois. By mid-century will be like that of New Orleans, Louisiana, and by the end of the century like that of Dallas, Texas, which we just talked about how many days we have above 100 degrees. I think this really indicates to you the extreme nature of how the world will change around us as a result of climate change. And of course, this has dramatic effects on health.